In this video, I will give a brief general introduction to high-dimensional statistics and big data. Big data is, of course, a huge buzzword. Everyone claims to have it, everyone claims to analyze it. But what actually are we talking about? Well, if you look at Wikipedia, it says datasets that are so large or complex that traditional processing applications are inadequate to deal with them. There's a classical characterization with 3 V's that may be familiar to you. So characteristics of big data are volume, the large amount of data that are available, velocity, data that are available in real time, and variety, many different variables and even of different types. So here would have numerical data, but also text or images and so on. There are many extensions to the V's, so there are lots more V's added actually if you look at more recent definitions. And if you if you want to have a look, do a Google search and you'll find lots of big data definitions. Now, to structure it a bit more, we could look at the whole process of big data and see what kind of steps we have that are needed if we want to analyze them. First, one thing that people look at is how to store and access such large amounts of data. And not only that, but also how to do that if data become available in real time. How do you quickly access new data and store new data? So this is very much, of course, a computer science problem and something that we will not be dealing with in this course. Then once you've stored and you can access your data, how do you then process them? So how do you make sense of the variety of data? How do you translate text or images into numerical data? Because in the end, we need to have numerical data to analyze. This is still much in the computer science direction. There is also some machine learning involved here. Perhaps some operations research could be useful here. Although it slightly touches in some aspects on statistics, we will not really focus on this either. What we will instead focus on is really the data analysis part. So once we've somehow made sense and processed our data such that it's in a numerical form, how do we now extract useful information from such data sets? And this is really where statistics and machine learning come in. And then, of course, there's another step, which is how do you, once you've done your analysis, how do you actually report it? I call it visualization. That's one part of it, but of course it's much more. It's in general, how do you report and interpret results? And of course, this is not just up to the people who do big data, but also to the actual applications and content specialists. Now, if you look at this scheme of 4 steps, you would often see this described as data science. So, of course, this is another vague term, but it refers to all the things we do in analyzing data. So the red part is what we will be focusing on in this course. So what is making analyzing big data different from other data? I think it's not such a clear-cut distinction, but if you want to make a distinction, it's that in what we call big data sets, again, we'll need to give that some more thought what they actually are, but both the data, that's the part we already looked at, but also your statistical model are not clearly defined. So in a traditional application, say, take a macroeconomics application, you have data on maybe GDP, unemployment, inflation, fiscal policy, you name your classical, relatively few macroeconomic series. And we have models linking them together. We have the Phillips curve, we have Oakland's law, and so on. Now, if we construct bigger data sets, we often have that many data sets consist of data which are generated as a byproduct of another activity. For instance, what we do online, we generate a lot of data there. But this data does, of course, not so clearly fit into these nice models. We can actually make data sets even larger and larger and do transformations and so on, which makes, of course, even more complicated to formulate nice theoretical models. And for instance, economic theory will not help us anymore building these models. And there's another issue, and that is that even though lots of data might be available, a lot of it might be garbage for our particular application. So the actual information that is present in the data is much less than the data we have. Now, of course, we can do a careful manual analysis and discard things based on theoretical arguments, but that's of course exactly what we don't want to do, because there may be stuff in this data that we had not thought about, and we want to get our statistical methods to get the information out of the data. But this becomes then sort of a needle in a haystack problem. We're looking for a small needle of information in a big haystack of data. And finally, another thing that makes a big difference to standard analysis is that computational costs are often much higher. If you have to analyze more data, it will also take more time. And so we have to be much more careful in thinking about algorithms and speed of algorithms rather than in a traditional statistical or econometric application. So let's look at some examples. For instance, we can look at a marketing example of maybe we want to analyze product sales. We are a company, you have sales for a certain product, you know the prices of this product, and you know promotions. And maybe you also have this data for a competitor product. And you want to try to predict sales based on past sales, prices and promotions, because based on that you could make, for instance, a policy about prices or when to use promotions and what kind of. So a traditional approach would just focus on these few series. Now, while that is certainly a sensible option, we could do much better, because if you probably have data for many products in your company. So there might be some that actually are competitor products, there might be others which are supplementing it, so they would tend to get bought together, and others might be unrelated. But we don't really know. If we have many products, we cannot really tell a priori how this will be. Maybe we have actually not just one store, but we have multiple stores. Maybe we have web shops. We have many different kinds of advertising. Maybe we look at not just traditional promotions, but look at how are things popping up on a web page. How many clicks do we have on certain links on our website? All these data you would have available. Now, clearly not all of it will actually be useful for predicting sales, but some of it will, and we don't really want to delete data a priori anymore. We want to use all of the information we have and try to let our methods decide on what is useful or not. We can also look at, say, finance, and we want to construct a portfolio of assets that mimics a certain type of return. So this could, for instance, be used to hedge a certain return. So we have something that we want to hedge, and we want to construct a portfolio that mimics that particular return. Now, we would typically have many assets to choose from. So how do we combine that? How do we choose those assets? Well, you could imagine that having too many assets is also not good, because you would have lots of transaction costs. You don't want to keep on rebalancing, so you would want to have a portfolio with a relatively small number of stocks. But how are you going to choose these? Are you going to use your knowledge a priori to choose them? But maybe you miss out some that actually could be super helpful. Are you going to start with a big set, but then you're not going to invest in all of these? So you want, again, to have methods which can extract the information from all of these assets, which ones are actually useful and which ones are not. And we want to, without any model in mind, let methods decide that can learn from the data. Now, a more traditional thing, as I already mentioned, is macroeconomics. Well, we can, of course, build theoretical macroeconomic models. We can try to estimate those using relatively few number of series. But we also know that those models are never complex enough to describe reality. I mean, reality is, of course, much more complex than macro. There are interdependencies among many series which play a role, both within countries but also across borders. Now, nowadays, there are much more larger data sets available. Of course, central banks have many more data, but also for researchers, there are large, what is called granular data sets available, which allow you to zoom in, which do not allow you to just look at production overall in a country, but look at production on sector levels and look at not just production, but many other sorts of variables. So how would we model such large systems? The relations are complex, we don't really know what the relations are. Well, one thing we could perhaps do is look for commonalities among series. If we know that many capture, say, real economic activity in one way or another, we would expect something like the business cycle to affect all of these series. And so we would need to have methods that can actually exploit this kind of patterns and find those in the data without assuming a particular model. Another example is something I've been working on myself and comes in the form of official statistics. Statistics Netherlands, or CBS in Dutch, they give their estimates of unemployment rates by using surveys. But these surveys are costly because it requires people to actually interview people in the population, and it of course requires depends that people actually want to fill out those surveys, want to take their time for that, and it takes time to process. So estimates are late, and this is something we of course see that these estimates come only during, for instance, the month halfway during the month later, which might be a problem if we need to build policies on them quickly. For instance, in the COVID pandemic, it would be great if we had very quick estimates of unemployment, so you could take that into account when looking at how to support businesses, for instance. Now, what you might think here is to use the big data approach, because if people get unemployed, they will likely search for particular information regarding their unemployment, such as how to apply for unemployment benefits. They will look for available jobs. Maybe they will look for advice on how to set up their job application, how to write their CV. So if we could have information about that, how often people search these things, maybe we could use that to produce estimates for unemployment. And we could do it in such a way that we would do it simple and timely unemployment estimates, because these data are available, for instance, on Google. And Google allows, they record frequencies, how often search terms are used. And these are available almost in real time. So you could get much earlier estimates, which we call nowcasting. When we are forecasting the present. So we're not doing in the future, saying what is unemployment now. But of course, then there's the question, how can we use this information? Because there's no model which tells us how searching for unemployment-related search terms actually feeds into actual unemployment numbers. And there are practical issues like which search terms should we consider. Some might be useful, other might not be useful. Even some that we know are useful will turn out not to be useful. For instance, I was looking at this in joint research with people from Statistics Netherlands, and one of the search terms which obviously seems useful is CV. But there was a strange seasonal pattern in CV, which was hard to explain, given that with people really in winter want to have more information about how to write a CV than in summer. Of course, once you realize that CV in Dutch is the abbreviation for centrale verwarming, central heating, then it suddenly makes sense that people in winter will actually search much more for the term CV than in summer. But obviously this is not in any way related to unemployment. So how can we come up with methods that can take these things into account? So as we will see in the course, traditional econometric methods are not suited for such analysis. So they cannot deal with the fact there's so little information that there's actually too many series, and they suffer from what is called the curse of dimensionality. So the next lecture will deal with this in detail. And this means we need to have new methods of data analysis, different methods, which you could say are purely data driven. So there's much less emphasis on models. Instead, we try to extract models from the data. These methods should be able to discard irrelevant information only based on the data, and they should be able to handle large amounts of data in an efficient way. So we also need computational efficiency. Now with these goals is actually what high-dimensional statistics and machine learning are about. So that brings us to the next question. What is the difference between high-dimensional statistics or machine learning? So this is a very complicated question to answer. So let me give some things that people have considered to be the difference. I think the most promising one, the most prominent one is that machine learning focuses on prediction, whereas statistics focuses on inference. So what you will see is in machine learning, there's really a focus on prediction. We don't care at all whether we use the right model, whatever model means in this context, as long as the predictions are okay. Whereas from a statistical background, you would often be not just focused on prediction, but also on learning about aspects of the model. For instance, which of your variables are actually important in predicting, rather than just the prediction itself. Related to that is the notion that some people say that in machine learning people only focus on the actual samples, whereas in statistics we focus on populations. So you could argue that prediction is saying something only about the particular sample if you don't want to generalize. In statistics we often do want to generalize because we want to say more than just the samples we have at hand. In addition, we also care about quantifying uncertainty in statistics, whereas in machine learning, this is much less of an issue. Again, these are not necessarily true, right? These are all just perspectives that people have on the distinction. So, in prediction, do you want to have prediction intervals? Or if you do inference, do you want to have confidence intervals, for instance, for parameters? And the final way to look at that is that some people say, well, in machine learning, we care about practical performance, which isn't a bit related, of course, to the other points. For instance, about the sample and how does it perform in your samples, which is practical performance. Whereas in statistics, it's more also about theoretical foundations. So can we say something theoretically about the methods? If we look at theoretical properties like consistency and these kind of things. I think all these distinctions are not very helpful. I think it's more trying to create a divide that maybe is not really always there. And it would be much better to actually learn from the different fields and bring out the good things together. So if you want to get into this debate, try Googling stuff like statistics versus machine learning, and you'll end up in tons of discussions where people discuss all these things. I want to instead look at things where we bring this together. And that is the field of statistical learning. So it's machine learning, but we do it from a statistical perspective. And we can get all the good things from machine learning, including the computationally efficient algorithms, and bring that to look at things from a statistical perspective. So the focus of our analysis is not always so clear-cut. So prediction is definitely useful sometimes, not always. Variable selection is sometimes useful, but again, not always. Quantifying uncertainty is sometimes useful, but not always. So it depends really on the type of application that we have, how we deal with this. So here are some examples based on the ones we had before. I mean, sales analysis. Well, if we just care about doing stuff like predicting sales, maybe we want to give recommendations to customers what product to buy, or on Netflix what movie to watch next. You probably don't care so much about uncertainty quantification. It would be quite strange if Netflix says, well, I recommend this movie to you, but actually there's a big interval around it, and it could be one of these 200 other movies as well. If it's wrong, right, if Netflix recommends you a movie that you don't like, well, you just don't watch it anymore, and you watch something else. So there's not much loss there if we don't take uncertainty into account. Variable selection is probably also not so important there. We don't need to know exactly which characteristics of you make you want to watch that movie. In portfolio replication, if you want to have portfolios of small number of assets, variable selection is crucial. It's not just prediction, but also variable selection there, because you want to have a low number of assets. Uncertainty also matters a lot, obviously, right? Because if you would happen to get your prediction wrong, and you're actually not hedging what you want to hedge. Of course, in macroeconomics, if you do forecasting, you don't care so much about these things. You really just are focusing on prediction. But if you do policy analysis, if you want to know how effective certain government policies have been, then obviously uncertainty is a big issue. If you do prediction for statistical agencies, then clearly, if you want to do it the proper way, and uncertainty would probably matter. On the other hand, if these predictions are not used to replace official statistics, but just as an additional tool, then you might say, well, we could probably just focus on the predictive part and not the uncertainty. So it really depends on each setting. And obviously, I add one more here. Suppose you would want to use patient data to find optimal medication or treatments. Then uncertainty definitely matters, right? You don't want to reach wrong conclusions there. So we will allow for all of these different kind of focus. We will look at methods which deal with these or do not deal with these, because for every kind of application there's a different focus that we have. So that brings me to the end of this introductory video. In the next one, I will start with the real analysis and focusing there on why standard methods are not applicable for analyzing big data or high dimensional data sets.